everyone, and welcome to VLSI for All, where we dive into fascinating world of technology, engineering, and innovation. I am your host Sanket, and today we are exploring a critical but often overlooked topic in chip design, EMIR analysis. Joining us is a true expert in the field, Bertrand Genere, Principal Product Engineer at Cadence Design Systems. Bertrand has spent years specializing in power integrity and reliability, ensuring the chips powering our devices are both efficient and robust. In this episode, we will uncover the importance of EMIR analysis, how it prevents unexpected failures in electronics, and what the future holds for power integrity in advanced nodes and AI-driven designs. So sit back and relax and let's get started. So Bertrand, how are you doing today?
Hey, hi. I'm very fine. I'm very happy to share some knowledge with you and the audience.
That's great. That's great. Sir, for beginners, could you tell us about yourself? And along with that, can you share us your journey stepping into the world of VLSI and EMIR analysis? What inspired you to specialize in this niche field?
Yeah, let's start with my biography, but I promise it will be short. So I was born in 1985. In fact, the same year than the Intel microprocessor 32-bit, which was called the i386, which is quite famous. So there were some background already with regards to integrated circuits and processor PCB and so on and semiconductor industry even before I was born. But still, so I was surrounded by technologies during my childhood. And I have had an interest in what is with regards to the future, to the technology, to sci-fi movies. And I was curious. It was a key in my story. So I was very curious to know how things work, such as computers, calculators, but also video games. For instance, my first console was a Nintendo Entertainment System. I played it. I was maybe 5 or 6 years, and I still have it. Look.
Wow, that's great. Like,
I kept it. And
yeah,
in a sense, it was a first experience with regards to the VLSI because you have the controller, right? So your inputs.
I
So
see.
you have
Yep.
different inputs connecting to the console, which contain the processor and some units such as image and sound processing units. And then you have ROM and RAM included in your cartridge.
Mhm.
And then you have some connectors connecting to your TV screen. So you have some protocols to provide sound and images and put it inside the television. It was kind of magic when I was 5 or 6 years old, but I was already experiencing these technologies. Let's say like this, and I was very interested in what's this magic, what's behind. So then, during high school, I did specialize in a scientific section with which means more focus on mathematics and physics compared to the other specialties. And in France, at 18, you have a final exam to pass after high school, which is called the baccalaureate. So I got it, and then I decided to move towards technology university. During 2 years, I did learn a mix of mathematics, physics, electronics, optics, computer science, a lot of things because I was not really sure at this time what I would like to focus on. I was very curious on various topics. And what did happen is that I did realize that I enjoy a lot learning about analog and digital circuits. That was my favorite lessons. And then I decided to continue with an engineering school with a focus on microelectronics. So it was composed of analog, digital, application-specific integrated circuits, field programmable gate array, FPGA, and MEMS, which is microelectromechanical systems. And during those 3 years in engineering school, I realized that ASIC was my preference. So I did apply for an internship at Cadence Design System, which was a EDA, one of the main EDA company, and I did join a digital designers team. And I was very happy there because I could start learning a lot with regards to advanced technology nodes. So at this time, it was in 2008, so it was TSMC 65 and 45 nanometers. And I was working on design rule checks, layout versus schematic, and DFM, design for manufacturability, within the team, and I did enjoy it very much. So the fact to be included in a digital expert team with different nationalities, very skillful and kind engineers, and it was very inspiring for me. And it paved the way for me to continue in the company as an application engineer. And I wanted to keep my knowledge quite close to transistor and silicon and physical effects. So I moved to power integrity analysis then. And it was for me a good combination of nanoelectronics, physics, computer science, and also a good way to perform analysis and optimization, not only on digital signals, but also on analog waveforms, power and ground.
Got it. Got it. That's nice. Nice that you still kept your Nintendo box intact along with everything. Along that. That's cool. Yeah. And so, like for those unfamiliar, can you explain what is EMIR analysis in simple
Sure.
terms and why it's so critical in chip design?
Yeah, sure. So EMIR acronyms, because there are two acronyms, it's composed of EM for electromigration, which is the quantity of electrons moving through your metal wires. And IR, I is for current and R for resistance. So IR is basically a voltage. So IR drop is voltage drop. What is the voltage within your VLSI circuit? So you divide it into nodes and equivalent resistors, and you do compute voltage at each point of your design. So this is to summarize EMIR. So this is electromigration and voltage drop analysis. And electromigration checks will consist of being sure that your current crossing the wire is not too high, because if you have too much electrons going through the wire, you will have some heating effect and mechanical stress, and you may end up with an open with a certain lifetime on your wire. So basically, some part of your design will not work as expected at the end. So that's it for electromigration. And for IR drop, so as I told you, it's a study of voltages within your chip power and ground network. And so we have to start from a place and route design. And the EDA tool, which is Voltus at Cadence, is using Kirchhoff laws to compute voltage on billion of nodes. And it's using, for the standard cells and memories, an equivalent model, which is composed of tap currents, resistor, and coupling caps. And then you can check that the voltage seen by the cell is not too much degraded versus the input voltage, because you need the cell, the standard cell or memory to operate correctly. And if you do have some IR drop, the quality of the cell is degraded, meaning that you have some extra delay to pass the information from the input to the output of the cell. So you do add some extra delay, meaning that you may end up with negative slack at the end because of IR drop. And even worse, if you have a big drop on a cell, you may have the cell not which will not have a functionality at all. So at the end, the output will be stuck at 0 or X. So yeah, that's basically IR drop and electromigration.
Can you like give a real world example of EMIR analysis, especially where it prevented a catastrophic failure in chip?
Something quite common is the fact that during your project timeline, the designer underestimates the power consumption of the chip. And the reason is that most often the RTL code is changed and the designer adds some functionalities to the chip. So this impacts the power consumption. And also, because you do optimize for timing your chip, it is at the expense of power consumption of the standard cells. So if you have too much current demand, at the end, the battery cannot sustain such value, and the chip basically will not work at all. So the first step of EMIR analysis is really to compute power accurately and give accurate calculation of the different components, so switching power and leakage power, to guarantee that your chip will work as expected. And another reason for chip failure I can think of is when you have badly placed the power and ground pad. You may have too much current demand on a specific pad, and then you will see electromigration analysis issues on the pad, meaning that you have too much current, and then you will have an open that will be created just after the pad on the wires, or the pad itself will not work as expected. And because of the package, you are limited in the number of power and ground pad you can have, so you have to be smart in the way you place them.
Okay. So like to me, electromigration and IR drops sounds like intimidating. Like how do they impact the devices that we use daily, like smartphones or laptops?
Basically, to be very simple, IR drop checks will guarantee that the chip work, that the device
Mhm.
will work at the end. If you do exceed the foundry recommended limits, because the foundry give you some limits for IR drop and electromigration, you do take the risk to have some functionalities of your device that will not work. It may be also only some functionalities because the power consumption will depend of your scenario, right? Of your simulation. So if you have some particular demand because of, I don't know, video sharing or video display, and you call a lot of standard cell at the same time in a local area, then you may have a big drop locally, and this particular function may not work. So this is what could happen on your device when sometimes for very process intensive queries, you may have not functioning devices and not the output you wanted to get. Also, you need to be sure that your device is robust enough, and electromigration may impact your device after a certain lifetime. So basically, the device will work during 1 or 2 years, but maybe then it will not work because you will have some opens that appear because of electromigration. What else can I say? Also, by examining and optimizing power, your ASIC will need less energy from the battery, and you do extend your battery life, and also you do reduce the usage. So when you think about your smartphone, that means that you have several functions. You can turn off some part of the design, so you do preserve your battery. And by optimizing power with IR drop analysis, you guarantee that you don't have to plug your smartphone into an outlet too often. So I think this talk to many people, in fact.
Great, great. That's a great insight. So like maybe just to make people interested in this field, can you tell us like for someone not in this field, what does a day in the life of an engineer working on EMIR looks like?
Yeah, sure. So let's think about a project timeline. So when you start a project, the first step for the sign-off power engineer will be to read the different documentations and preparing the inputs for sign-off checks. And it may be hard already and difficult to have a good understanding of the limits for advanced nodes. So you have to read carefully the document and be sure that you set up your tool to ask for the proper limit before starting the analysis. Um, you must parse not only the Foundry directory, but also the IP provider directories to get information. And you need to gather the different part of the puzzle, meaning that you need to have the different inputs for the different analysis, IR drop, electromigration, and the other ones. And you often need to ask for missing inputs to the consumers or providers, such as a SPICE netlist, or it can be GDS. It can be specific .libs with embedded voltage waveforms. So this is the first part for a sign-off power engineer, and it's already a big part. The next step is during a synthesis of the design. The designer will need you to do some power estimation of the RTL structure. And here, the difficulty is to get mature enough data to have meaningful results in terms of power. Um, so the aim is to drive designers towards a better architecture for power. And the EDA tools that are used at Cadence is Genius for synthesis and for Joule, and it's Joule for RTL power estimation and optimization, because our tool Joule can also give some hints to designer how to limit the power consumption of your RTL.
Mhm. That.
Then there is another step. So when you have a place and route design, you must deal first with shorts between power and ground. You must deal with overlaps of cells, because when the backend designer start with the floor planning, of course, there are some mistakes that happen regularly, and you have to have a close relationship with the backend engineer to pinpoint those issues and fix them. Then, when your power and ground network is good enough, you can start the analysis. So you will start with the static airdrop analysis. So you take the average power of your chip and you deduce the average voltage seen by the different cells, and you compare it to the threshold given by the foundry. Usually it's something like 5% of nominal voltage for VDD plus VSS. Once you acknowledge the static analysis, so once you fix some missing via, for instance, or some issues like that, you can move towards dynamic analysis. So here, instead of having an average current, you look at the dynamic currents, so current waveforms for each cell. And then instead of having a map of IR drop, you will have a movie showing you the voltage drop with time. So you can really look at the scenario and which cells are having troubles at which time. So this is a more consuming analysis in terms of runtime and memory usage. And this is something you do when you have something more mature in terms of placement and routing. And here the threshold is different for dynamic. Usually it's 15% of nominal voltage for the peak voltage drop. And if your IR drop exceeds this limit, you have to take actions and strategies to decrease the IR drop. One example I can give is that if for a specific scenario you have some neighbor cells activated at the same time, then you try to spread them to limit the peak current locally. That's basically my job.
Wow, that was a very detailed and a good explanation. I hope this inspires some of our engineers to explore this area too. But like, what are some common misconceptions that engineers or companies have about power integrity and reliability?
That's a very good question. I think with regards to power integrity, the main mistake is to consider that it's just about power. It's true that we do analyze power in watt. We do analyze leakage power, switching power, internal power, and glitch power. And with our tool, with Voltus, we have also the capability to do a profiling of your simulation and determine which start and stop time of the simulation we should take, which is more meaningful for power consumption. So power is part of power integrity, but it's not the only thing. I told you already about IR drop analysis, so voltage drop, and electromigration. So this is part of power integrity too. But beyond those analyses, there are plenty of other ones. There is also what we call rush current analysis. So you may have a design with always-on domain and switchable domain, meaning some part of your design can be turned off, then turned on. And for this purpose, we do use power switch to activate the block when need be. And you need to check what is the peak current when you activate the block. Because if you do activate all power switch at the same time, you will have a huge peak current and a huge voltage drop causing troubles. So you need to activate the chain of power switch with a certain delay to limit the peak current, to flatten it. So you need to find out the good trade-off between rush current and the time to make the block available for reading the inputs and giving outputs. So this is rush current analysis. We have also what we called electrostatic discharge analysis. So this is with regards to reliability. For reliability, we don't talk only about yield on your wafer. We talk also about the quality of your chip under when you make it when you use it in reality. So first, when you use it within the package, you may have some electrostatic discharge when manipulating your chip. So you need to check ESD. And also with regards to electromigration, so it's really part of reliability, and it's something that happen after a certain lifetime, as I told you before. So those are two concepts that are linked to reliability, and also with advanced nodes. We have also FinFET process, and for this process, we have some temperature elevation that we need to take care about. And we do what we call self-heating analysis that is also linked to reliability. And then there are also some special ESD analysis depending on the application. So if you're in automotive market or aerospace market, you will have more analysis to perform and more restrictive ones.
And do you think like this kind of specialization and EMIR engineers are like demanded, particularly in like all the semiconductor companies other than Cadence? Or like, can you like list some of the companies that like are interested to have these kind of engineers in their team?
Basically, in the semiconductor industry, any chip designer needs power integrity analysis. It's very important. It's part of the
Mhm.
full flow for ASIC. Um, as I told you, for Cadence or EDA tool for sign-off IREM is Voltus, and it's used by many companies such as it can be a MediaTek, it can be ST, Microelectronics, NXP, lot of companies worldwide, from emerging startup towards big companies are using such a tool to guarantee a good functionality of their chip. Also, the foundries are using the tool to are validating the tool. We have a partnership with TSMC, Global Foundries, and so on. So, and I think it's more and more at the heart of semiconductor, because with AI, for instance, we have a lot of power demand when querying something on the prompt, and the system itself is very high current demanding. So I think there are a lot lot of analysis to come and to improve in the future with regards to power, IR drop, and electromigration for sure.
So talking about future, in this era of AI, machine learning, and like 3D ICs, how do you see the future of EMIR analysis going to like evolve in next decade?
In fact, the movement is already visible. We
Mhm.
don't talk because nowadays we don't talk only about electrical analysis. We talk about co-electrical thermal simulation. So it can be easily explained because when you have 3D IC, you do stack several chips, several ASIC or HBM, and you have a temperature elevation quite easily in this situation, and you need to be sure that the current demand of the chips do not impact the temperature elevation too much. So we need to optimize the floor planning of the system in such a way that the power density do not impact too badly the temperature map. We have a tool for temperature analysis, which is Celsius at Cadence, and both Voltus and Celsius are used in combination to do co-electrical thermal analysis in 3D IC design within a big cockpit, which is called Integrity 3D IC. So this is our tool for 3D IC. So this is for the 3D IC part. The other part is about artificial intelligence. With artificial intelligence, the chip size and complexity did increase a lot. You had a visible show at CES recently with Jason Wang showing a giant chip, and you see how complex can be now the system with AI. So we need to improve regularly the runtime and memory usage capacity of the EDA tools. And we did improve Voltus with time, from multi-core to super threading to hybrid computing to cloud access. EDA tools are now accessible through cloud, and you can ask for big data center machines to compute the simulation. So this is one big part. Here I'm talking about some low light and how we need to deal with it, but there are also some highlight because with AI, we also have a way to improve the EDA tools. For instance, Voltus moved to Voltus AI. So this is our last version. So it's called Voltus Insight AI. And in fact, we do combine Voltus inside the place and route tool, and AI is used to do some automatic fixing based on IR drop weakness. So the tool determines IR drop weakness, and we have some automated IR drop fixing by adding via, shapes, stripes, and doing some automatic placement optimization, and so on. So AI is also a good opportunity to improve the designs.
So, like to just summarize everything, like could you give one piece of advice to students or young engineers who are aspiring to work in this domain? What would it be?
Yes, so maybe start with a tiny block composed only with standard cells because the flow is quite quite big. There are a lot of analysis to perform. So you need to start tiny to have a good understanding on the script to be used and what are the part of the flow. This is my first recommendation. Another piece of advice would be to have a good understanding of SPICE netlist and SPICE simulation. We have a Spectre for this at Cadence, which is a tool that is doing a simulation. And this will help you to better interpret the results, the IR drop results, and check the results by SPICE simulation if need be. Then, when you are working on the project, you must learn from designers the behavior of the chip. You need to well understand the different scenario to determine where and when you will have a lot of power consumption to do the proper analysis for IR drop. So this is my advice with regards to IREM, but more globally, I want to give some advice to any designer that start in VLSI. I would say think about this, past, present, and future. So past, use the knowledge from experienced designers that are already in the company. Read some book about the story before you arrive on a tool or a project or whatever with regards to IC. You can read some previous manuals, for instance, or whatever, to understand from where it started and why you are at this point. So this is for past. Present, make a checklist of the analysis to perform and focus on one task at a time, focused on your present tasks, and talk regularly also to the team to be informed of any design change that could impact your analysis. This is very important, and talk regularly to customer, to R&D, and so on. So this is for present, and for future. Follow the high-level company informations, the highlights, the semiconductor news to see the trends and how it could affect, in fact, your job. I mean, the trends such as artificial intelligence impact both the way we work, but also the work itself. So you have to stay tuned on the coming trends so you're well prepared for the future.
Awesome. That's really good advice, especially when this field is very new and there's not much of experts to shed light upon this. This advice and this analogy of past, present, and future definitely is going to help some of our young engineers. So that's a wrap for this episode. A big thanks to you, Bertrand Genere, for sharing your expertise and insights into critical role of EMIR analysis in chip design. We hope this conversation sheds light on importance of power integrity, IR drop, electron migration, and how they impact the technology we rely on day to day. If you enjoyed this episode, don't forget to subscribe, leave a review, and share it with your network. Stay tuned for more fascinating discussion with industry experts. Until next time, keep exploring, learning, and innovating. Thank you. Bye.